Alright, hello class. In this video, we're going to be talking about divergence and curl. And what these things are basically just measurements of a vector field on a pointwise sense. They're very similar to circulation and flux, except instead of measuring things over a path, they measure things at a point in the vector field, and specifically what's going on at each point within the vector field. Okay, so to just have this written down, divergence and curl are pointwise measurements of the vector field and are similar to flux and circulation. So whereas flux and circulation are measured over a path C, divergence and curl are going to be just measured over a single point. Okay, say P. Okay, so what exactly are these? So we're going to start with divergence because it's typically the simpler one to talk about. And then we'll talk about curl. Okay, so divergence, it essentially measures a vector field's tendency to expand or contract. And this is sort of, you can think of it on a microscopic level. I'll talk about what I mean in a second, but on a pointwise level. So you can think of this as flux density, i.e. how the amount of flux entering or leaving a point. Okay, so what exactly does that mean? But if we go back to what flux is, okay, and we consider it over, say, a counterclockwise curve, we have a few options here. Right, so if we, let's say, have this this path here, C, and suppose on one side we have vectors sort of pointing in this way, and on this side vectors pointing in this way, this is positive flux, right? There's more flux entering the region than there is exiting. So what divergence measures is sort of the same thing. We shrink the curve down to a single point, okay, and measure, well, how much, let's redraw that, say how much the vector field changes from moving into this point versus exiting this point. So here we see that there's more vector leaving the point than entering. In other words, something about this point is causing either an increase in speed, maybe it's a booster point, or an increase in volume, or whatever it is this vector field is measuring for us. This is what we call a source, right? Because this point is creating more vectors. All right, and this is what would be considered a positive divergence. So, like I said, these do calculate or measure similar things. Flux is talking about what's happening over a path or over a region or, you know, over, say, just a path, right? Versus the divergence, which takes that idea and shrinks it down to a single point. Okay. Similarly, if we have, say, vectors entering this region here, but then way smaller vectors are leaving on the other side, okay, and we shrink that down to a point, this is negative flux, okay, which leads us to, say, something like this happening on a point, which is a very large vector enters the point, and then a smaller vector leaves. Okay, this is negative divergence. And this is what we call a sink. And we call it that because, well, something's happening here. If this is water flowing across here, and maybe it's the amount of water, as we cross over this point, we've lost a lot of water, right? There's maybe a hole here that sucks a bunch of it up. Maybe this is fluid flow, and this is a hill, right? A hill starts here, so the velocity decreases by a lot. This is considered a sink, right? Since the point is reducing the magnitude of the vectors. And I should say here, I fixed it, but this point isn't creating more vectors exactly. It's creating, well, more of a vector, but it's really creating more magnitude. Okay. And then how we have zero flux is essentially if the amount entering is the same as the amount leaving. Okay, so that could be zero flux. Or we could have a situation where there's no entering or leaving at all. And if we shrink that down to a point, that would be something like the point doesn't really affect the field at all. Right, so this would be zero divergence, where we'll have no source or sink. We will call this source free because the point basically doesn't really do much. Or I should say the field is unchanged across the point. Okay, so that's what we mean when we say that this measures how much a field tends to expand or compress. This would be expansion with a positive divergence. This would be compression, right? Which comes from a negative divergence. And this would be neither, right? Neither expansion nor compression. This is just unfettered flow, essentially. It's unaffected, okay? Usually if a field is source free, we say that it's partially part of what we would call ideal flow, meaning that it's flowing naturally and it's not like compressing or expanding. It's not being affected in sort of any way. You can almost think of maybe there's a blockage here, right, at this point. Okay, so let's talk about how we actually calculate this, because this is something that isn't always easy to just see on a graph. Sometimes it is, sometimes it's not. Okay, so the divergence of the vector field f, little f, little g, little h, so we're going to look at this in 3 dimensions, mainly for the calculation base, but for most of our examples we're going to be looking at 2-dimensional vectors. But this is given by this formula here. We notate it as div f, divergence of f, and it's calculated using the operator we use for the gradient, right? We take the gradient operator, which is called nabla, okay, and we dot it with f. Okay, so it's the vector. If you remember what this gradient operator is, it's the partial derivatives, right? So it's the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. Okay, and then we're going to dot it with capital F, which is little f, little g, little h. And we're taking the dot product. So instead of multiplying here, this is actually kind of odd. Instead of multiplying, we're just applying the derivative as we would a dot product. And if you remember what the dot product does, the dot product tells you kind of how much energy one vector gives to another in its original direction of travel. You can kind of think of that here is, well, how much is the f component, how much is the x component changing in the x direction? How much is the y component changing in the y direction? And how much is the z component changing in the z direction? Because when we put this all together, we're going to get a partial derivative with respect to x of f plus the partial derivative with respect to y of g plus the partial derivative with respect to z of h, or f sub x plus g sub y plus h sub z. Okay, one thing to note here is that this is what we tend to ignore in that thing we do for checking conservative vector fields, right? We would have the f sub x, g sub x, h sub x, f sub y, g sub y, h sub y, and f sub z, g sub z, and h sub z. This main diagonal here, we usually ignore when we are checking if a vector field is conservative, but we use this diagonal to find the divergence, right? So this diagonal is still used just simply to calculate divergence, interestingly enough. Okay? So thankfully, this is a pretty easy formula to deal with. You just take the x derivative of the x component, the y derivative of the y component, and the z component, or the z derivative of the z component. Okay, let's look at some examples for this first one. This one we should expect, well, we should get what we expect. So we're going to start simply with the vector field capital F equals xy. This is the explosion vector field. Okay, and if we remember what that looks like, basically it's sort of exploding outwards in this manner. So we, just based on the way this looks and what we've been told about what divergence does, we should expect a positive divergence. So when we calculate this, div f, remember it's little f of sub x plus little g sub y. Okay, so that's going to be, well, here's our little f, or little g, f sub x, that's 1, g sub y, that's 1, we get 2. And that's exactly what we expected. We have a positive divergence. We have expansion. All right, we can see it here with expansion. Do keep in mind, though, that it's not always so much a vector entering versus a vector leaving. That's more of a way we can intuit what's going on. And it's a good way to visualize what's happening here. Okay? Okay. Before I go to the next example, though, this vector field is full of sources. Every point is a source. Okay? Because we just got 2. So we have a divergence of 2 at every single point. So that means that we're expanding at every point. We get expansion at every point. Okay, so now for this next example, let's say we have the vector field g equals xy, comma, x squared minus y, comma, z. Okay, so div g, again, it's little f sub x plus little g sub y plus little h sub z. Right, so the derivative of xy with respect to x will be y. The derivative of x squared minus y with respect to y is -1. And the derivative of z with respect to z is 1. So we get y as our divergence. So notice that the divergence at any point, so keep in mind that this is a function of x, y, and z, but it actually ends up just being a function of y. So what's going to happen here is Okay. As we increase in y, our divergence is going to get higher and higher. Okay, so say here if this is y equals 1, along this path, above and below or wherever, we're going to get the divergence of g is equal to 1. Whereas here, we're going to get the divergence of g is negative 1. Okay, along this path. So let's try and take a look at this. Three-dimensional vector fields aren't as easy to visualize as two-dimensional, but I'm just going to look at a couple values of z. What you'll notice is there are no z's in the x and y coordinates, so really we're basically stacking this same vector field on top of it for each, well, no, I shouldn't say that, sorry. At each level of z, we're going to get a specific vector field in 3 dimensions. I'm going to look at when z is equal to 0, just to give us a nice look at that. All right, if we take a look at this graph here, here's the vector field just on the xy plane, where z is equal to 0. Okay, and if we look, say, here along the y equals 3 line, okay, there I put it in orange, but as you can see over here, that the vector entering this line and leaving this line at each point seems to be extending in magnitude. Okay, it's not as easy to see on the graph here, but when we go out here, it's maybe a little easier to see that we get expansion. But if we go down here to, let's say, -3, okay, what we'll see is that the magnitudes of the vectors are decreasing right around here. Okay, so we would get a divergence of -3 along this, all the points along this line, while we got a divergence of +3 at all the points up at 3. So that's what this is measuring. If across points is are the vectors expanding or contracting, and the higher the numbers, the higher the expanding or contracting becomes. And you can kind of see this here at 4.5. We have what looks like expansion along these points. Okay. All right. So let's look at another example. Okay, here's one of my favorite examples. Capital F equals sine of pi x, comma, sine of pi y. So the divergence of f will be little f sub x plus little g sub y. Okay, so here we're going to get pi cosine of pi x plus pi cosine of pi y. Okay, now when we do this, what I want to mention here is that notice at different points we're going to get interesting values, right? If we put in 0, 0, what we end up with is cosine 0 of sine 0, right? So we'll get pi times 1 plus pi times 1, so we have 2 pi. Okay, when we put in the 0.11, let's say, well, we're going to get cosine of pi, so that's pi times -1 plus pi times -1, so we end up with -2 pi. Oh, what does that tell us? Well, we've moved from expansion to contraction, and if we do something in between, like let's say, I'll do it over here, the divergence of f at 1/2, 1/2, well, pi over 2 for cosine is 0, so we're going to get pi times 0 plus pi times 0, so we get 0. Okay, so if we were to think about this on a graph, at here we have the divergence is 2 pi, that's expansion. Okay, at 1/2, 1/2, we get 0, which is source free, nothing's happening. And then at the point 1, 1, we get negative 2 pi, which is compression. So what's happening is along this line, the divergence is decreasing down to 0 and then increasing back up to, decreasing all the way down to negative 2 pi. And then if we go all the way up to 2, 2, the divergence will be back at 2 again. Okay, so let's take a look at this on a graph. All right, so here's the vector field on a graph. I'm going to zoom in more to what we were looking at here, which is, say, 0 to 2, this grid here. And we see here at 0 that the vectors are all expanding away from the point. That's another way to kind of tell that you've got positive divergence. Right, and then what happens is, here's the point 1, 1, so we're getting expansion all the way to a sink, which is compression. So you can kind of see that there. Let me reduce this a little bit. Okay, just a little. So you can kind of see that, yeah, the vectors are getting, say if we look along this line, they're getting higher magnitudes, then they sort of like level out, and then they start decreasing again until we get to the point 1, 1. And we can notice that all these vectors are heading towards the point 1, 1. So I think this is a great example of what a sink can look like. All the vectors are being attracted to it. And but here 0, 0 is almost like a repellent. They're all moving away from it. Okay, so that I think is a great example of what, say, a source can look like, a place that's source-free, and a sink, what those three sort of concepts look like. Okay, so next up is the curl, and the curl of a vector field measures its tendency to rotate at each point. It's similar to circulation. Okay, similar to circulation, just at a point. Okay, so I'm going to show this in terms of 2 dimensions to begin with, but this one's a little more complicated in 3 dimensions, but it's similar. Okay. All right, so let's, like we did with flux, take a look at circulation and take a look at how these translate when we shrink them down to a single point. So when we were talking about positive circulation, you'll remember that's when the vector field aligned with the path, at least for most of its life, or you can think of it for all of its life. So if we start shrinking that down to smaller and smaller circles around, say, the point that we're talking about. So let's say here's our point and we have a very small path around it. Right, very small path. And the vector field has a positive circulation around that path. As we get the circle smaller and smaller to maybe even the point where we can't even see the path for the point, but we still get that movement that matches the path. Okay, what's happening here is the field wants to make a tendency for that point to revolve counterclockwise. Okay, so if we're causing a counterclockwise rotation at a point, that is positive curl. That's what curl is measuring, right? Curl measures the tendency of the field to cause rotation on a point-wise scale. So this field, if we shrunk this path all the way down to the point and we were still getting this sort of positive circulation at smaller and smaller paths around this point, we can expect that point to rotate. I like to think of this as being like a miniature paddle wheel, right? If this were a miniature paddle wheel, this field would be causing the wheel to turn around in a counterclockwise direction. Note, I'm going to start using CCW as counterclockwise, we're going to be talking about this a lot, counterclockwise versus clockwise. On the other hand, what gave us negative circulation is when the path went against, went against the direction of the path. Okay, so if this path is around the point P that we're looking at, and we do the same thing here, we put a very tiny path, okay, around it, and we're going in the opposite direction as before, we can hopefully see that this is more of a clockwise rotation. Okay, so this was a negative circulation, and when we shrink that down to a point, this gives us a clockwise rotation, and that is what we get with negative curl. Okay, what about zero circulation? Well, zero circulation, there were two possibilities, really. It was either the entire vector field was perpendicular to the path, so this would be more like a positive flux, or the same amount of the path was going against it as it was going with it. Okay, so something like this. So if we shrink that down to point size, okay, so for this one, the whole thing would be, say, perpendicular, right? And it doesn't look like this would cause any rotation, and it shouldn't. It acts more like a source, okay? The other way would be if we have the same amount against as we do with, okay? So if I put something that direction, it would be that direction. So it almost, when we shrink it down, becomes like a source, and in both cases, really, right? It's acting more like a source. So zero circulation comes out to correspond with zero curl, which is no rotation. Okay, and the curl of the vector field, capital F equals little f, little g, little h, is given by this calculation. So before, what we did was we took the dot product between the gradient operator and f. Now we're going to take the cross product. So we notate this as just curl of f, okay, is the gradient operator cross f, right? So it will be the cross product of the vector derivative with respect to x, with respect to y, with respect to z, cross the vector little f, little g, and little h. Okay, so it will be I, j, k. We're going to set up our cross product like we normally would. So in this row, we're going to put the gradient operator. And then in the third row, we're going to put f, g, and h, and then we'll copy down these two columns like we normally do when we find a cross product. Okay, so we'll start with the I component. So it will be the y derivative of h, so h sub y, minus the z derivative of g, Okay. Then we'll do the j component. So that is going to be the z derivative of f, okay, minus the x derivative of h. And then we'll do the k component, which will be the x derivative of g minus the y derivative of f. Okay, so there we go. There is the curl of f. Notice this is actually a vector, right? The curl of f is the vector h sub y minus g sub z, comma f sub z minus h of x, comma g sub x minus f sub y. Okay, what exactly does this give us? Well, notice that it is a vector in 3 dimensions. Okay, so this is a 3D vector. So remember, a vector is composed of 2 things, a direction and a magnitude. Okay, so the direction of the curl of f gives the axis of revolution at each point. Okay, while the magnitude corresponds to the speed of rotation. Okay, so what this means is that what I mean by the axis of revolution is that if we have this as the curl at a certain point, okay, imagine using our right hand rule, right? So if we karate chop this vector such that we want our thumb, well, let's not karate chop the vector, but let's take our right hand and have our thumb point in the direction of the vector. The way we curl our fingers is going to be the positive orientation of revolution around this vector. So that is what I mean by the axis of revolution. And if the magnitude, say, is doubled, we're going to be rotating around in the same direction, but faster. Okay, so this would be faster rotation. Okay, and so if I take this vector and flip it around in the opposite direction, well, now when I match up my thumb with this vector using my right hand, the way to match or to create the angle, right, if I want to curl my fingers, they will curl in the opposite direction. Okay, so if we were, say, looking at the plane here, it would be spinning around it this way. Okay, I think a better way to talk about this is to look at a graph. So let me show you a graph with various different axes of rotation. Okay, so here's a little graph I put together to kind of show what's going on here. When we're talking about the curl, I'm just looking at the point 0, 0, 0 here for simplicity. And this vector I'm representing as the curl. Okay, so if we think about, here's our positive x, positive y, right? So if I look at this from above, notice that this vector is literally just k. It's the vector pointing in the positive z direction, and I'm letting this guy rotate counterclockwise. Okay. So this is what I mean when I say that this is representing how it revolves around the axis of revolution. Our vector is an axis of revolution. Now, if I increase the magnitude of this vector to something like 5, you see now the speed of rotation is increasing, but it's still counterclockwise around this vector. Now, if we now switch this around and let it go to -5, notice that if we look at it from above in the positive z direction, we are going counterclockwise. However, if we flip it around and look over it at the direction, like from the -z, it looks like it is going counterclockwise. Right? So that is what we mean when we say that this follows the right-hand rule, that it always rotates in a positive orientation around this vector as an axis of revolution. Now, this is just curl vectors pointing in the z. We can change them. Right? For example, if we have something like this, if I start moving the plane around this way, and so notice what I'm showing here is a normal vector, and here's the plane, and this little vector is continuously revolving around this axis of revolution, okay, and with a positive orientation. Okay, so no matter how we change the way that this axis of revolution behaves, we're always getting positive rotation around the vector. All right? And so this is essentially what the curl gives us. Okay, is something like this. And so the higher the magnitude, the faster the rotation, and wherever that vector is pointing, that tells us in what orientation we're revolving around. Okay, so that's essentially what this vector gives us when it spits out a vector. But another thing to notice is these values here should look familiar. In fact, these are all the values that we check when we're trying to check that a vector field is conservative. Right? So for example, if I go back to the table again, f sub x, g sub x, h sub x, etc., right? And get rid of that main diagonal here from our normal table, we'll notice that the pieces that we use to compare for checking conservativeness are the same things we get here. The gx minus fy is here. The fz minus hx is here. And the hy minus gz is here. So it's almost like we're doing this, right? I, j, and k. As far as hy minus gz, fz minus hx, and gx minus fy. Okay, so notice that f is conservative if all three of these things are equal. Okay? And if all three of these are equal, then the curl of f will be the vector 0, 0, 0. So conservative vector fields have no rotation. Okay? This is also sometimes called irrotational. Or you could say rotation-free. That's what I prefer to use, rotation-free. So that's another property of conservative vector fields. If you want to check that a vector field is conservative, you're essentially showing that the curl is equal to 0. Okay, so this is the, say, 0 vector. All right, another thing to note that simplifies this for us is that the curl of two-dimensional vector fields will always be of the form 0, 0, g sub x minus f sub y. And the reason for that is, and if it's two-dimensional in a different way, then it will be the other thing. But if we're talking about vector fields on the xy plane, the only way we can rotate around a point is either, say, counterclockwise or clockwise. So that means that the only possibilities are vectors pointing in, say, the positive z, right? So something times k, I'll say c times k, or pointing in the negative x or z axis with, say, a d times k, and I'll call that a negative dk. Okay. Yeah. So, and if we go back to the graph that we were just looking at, all right, this is what we see. If my axis of revolution is pointing in the positive z direction, then we are just rotating counterclockwise, okay, on the xy plane. And then if we make the z negative, then we are rotating clockwise on the xy plane. Okay, so because of that, for two-dimensional curl, we tend to just reduce it down to that g of x minus f of y. Okay, so for simplicity, for 2D vector fields of the form little f comma little g, we reduce the whole idea down to just the g sub x minus f sub y. And then what this gives us is that if the curl of f is positive, this means we have counterclockwise rotation. Whereas if the curl of f is negative, this is clockwise rotation. Okay, so here for counterclockwise, this would be a positive curl. And here for the clockwise rotation, that would be negative curl. All right, so let's look at a couple examples. Let's look at, or find the curl of capital F equals negative yx. So for the 2D ones, it's actually a much quicker calculation. The curl of this f, that's going to be g sub x minus f sub y. Well, g sub x minus f sub y, well, g sub x will be 1 minus f sub y, which will be negative 1, so we get 2. Okay, now this is positive, so this implies a counterclockwise rotation for the entire field. All right, so if we remember what this field looks like, this is our rotation field, right, where we have macro rotation around the origin. Okay, so we would expect to get miniature rotation at every point. Okay, so I do want to mention that this is not talking about we're not talking about here, okay, maybe that's a better drawing. We're not talking about macro rotation, right? If you were to drop a rubber ducky here, it would tend to want to rotate around. This is the macro rotation. Okay, that's not what we're talking about. What the curl measures is that at every point, it has a tendency to want to rotate counterclockwise. So as this rubber ducky will be spinning around, okay, it will also be rotating, spinning in place. So macro rotation, I like to think of as, say, the orbit of a planet, right? The orbit of the Earth, for example, around the sun. Okay, so that's the macro rotation. The curl represents how the Earth rotates on its axis, okay, as it spins around its orbit. Okay, so it's measuring the orbit. So the curl is the orbit. Or no, sorry, not the orbit, but the actual rotation. While the macro rotation here, this would be the orbit, and this would be the rotation around the axis. Okay, now I really do want to show that this is not, these aren't always the same thing. We don't always get macro rotation and micro rotation at the same time. For example, let's consider this vector field here, just capital F is equal to y comma 0. Okay, well y comma 0, when we calculate the curl, right, so remember that's g sub x minus f sub y if we're talking about two-dimensional curl. G sub x, well g is 0, f is y, so g sub x is 0 minus the derivative of y, which will be 1. So we get negative 1. So we're getting a negative curl, so we should get clockwise rotation everywhere. Okay, but what does this vector field look like? Well, we have, let's say we're on the xy plane here, okay, and we always have the vector 0 or y0. So when y is equal to 0, so here y is equal to 0, we'll get the vector 0, 0. Okay, that's not very interesting. Let's instead look at the line y equals 1. Along the line y equals 1, we'll have the vector 1, 0. Well, 1, 0 is this vector. It points 1 in the x direction and doesn't move up or down in the y. So all of our vectors are doing this. Okay. Then at the line, or along the line y equals 2, we'll get the vectors 2, 0. So these vectors are behaving the same way, they have double the magnitude. Okay, and so here when y is 1/2, we should get vectors that are 1/2 the magnitude. Right? These should all be the vectors 1/2, 0, etc. And then when we move down to, say, negative 1, well, now they're going to be pointing in the negative x direction. Right? These are the vectors negative 1, 0. So notice that we don't get rotation in the macro sense. Right? No macro rotation that we can see. It's not obvious. Right? Because it looks like if I dropped a rubber ducky right here, or a little rubber boat, it would just travel along indiscriminately. However, if we zoom in on a point, okay, so let's zoom in on this point here. So here's our point. Then here we have the vector, this would be 1, 0. And now here's the kicker. Right next to it, right above it, we will have a vector that is slightly longer. I'm exaggerating it here, but this might be like 1.1 or something. And then right below it, we will have a vector that is slightly smaller. Okay. So if we had a paddle wheel at this point, we're getting more force up top, pushing this way, than we are on the bottom. So it's going to want to push the paddle wheel this way. Probably slowly, but at every point we're going to be seeing rotation in the counterclockwise direction, right? And that negative 1 means that it is going to be pretty much half the speed of the previous vector field we found, which we had 2. So the guys here should be spinning twice as fast as the points in this vector field, okay, and in the opposite direction. All right, so here, just to give an example of how we do this in 3 dimensions, the math is a lot more complicated. However, it's basically finding a cross product. Now, what I'm going to do to find this cross product, now that we've been using our little table of values, this guy, the fx, gx, hx, fy, gy, hy, fz, gz, and hz, what I'm going to do is find the cross product this way, where I have I, j, k, whoops, k. Okay, so the curl of f is going to be, in my I component, it's the hy, h sub y, minus g sub z. Okay, in the j component, it will be f sub z minus h sub x, and in the z component, it's our normal g sub x minus f sub y. So let's see what we get here. H sub y, let me label these. Here's my f, my g, and my h. Okay, so h sub y is going to be 0 minus g sub z, which will be x. F sub z will be 0 minus h sub x, which will also be 0. And then g sub x will be z minus f sub y, which will be negative 2y. Okay, so we get the vector negative x, 0, z minus 2y. Okay, so that is our curl. Now, what does this mean for us? Well, it's going to depend on different points. So at the point, let's say 1, 1, 1, right, just to help us out here, the curl of f at 1, 1, 1 will be the vector negative 1, 0, and then 1 minus 2, which will be negative 1. So it's the vector negative 1, 0, negative 1. Okay, so let's say we're just sitting out in space here. I'm not putting the axis because I don't want to make it too cluttered. But say we're at the point 1, 1, 1. Okay, then here is the vector. Where is it? Here we go. Here's the curl that we got. Negative 1, negative 1, negative 1. Okay, and what that means for us, let me at least orient us in the z direction here. Actually, let me do all of them. Okay, now these aren't, don't think of these as the actual axes, right? We're at the point 1, 1, 1. These are just the directions. Okay, I'm just trying to orient us a little bit as to what this vector is doing. Okay, but it goes negative 1 in the x direction, 0 in the y, and negative 1 in the z direction. And now if I create the plane that corresponds with this, what's happening at this vector field, okay, is that we're getting rotation around this vector as our vector, or as our axis of revolution, right? So this point is going to want to rotate in this orientation around this vector. That's what the curl gives us in 3 space at each point. So at each point, okay, we're going to get a different, maybe vector pointing in a different direction with a different magnitude that will correspond with the angular velocity. All right, now that's pretty much all I really want to show you when it comes to divergence and curl. Okay, that should get you rolling on the homework. And now we're going to show in the next lesson how these ideas relate to one another, how the flux mathematically relates to divergence and circulation to curl, and a really nice way to calculate line integrals, provided we have a specific setup. All right, so I will catch you all on that one.